Hey everybody! So this is the first section of Unit 1. So if you didn't watch that really brief introduction video that I posted, you might want to watch that just because it tells you a little bit about kind of how I do things and how you should take notes and what the learning goals are all about for this unit. So this video is going to strictly be on significant figures. So you have never heard of significant figures before in all of your 15 to 18 years of existence in all of your math classes is because a lot of your math classes don't deal with measurements. In chemistry class, you're using graduated cylinders and you're using scales and you're using volumetric pipettes and beakers and all that. And you can't be 100% certain about the measurement of something that you find. You can't be 100% sure about the volume of liquid in a graduated cylinder, or the scale is not 100% accurate about what it reads to us. So that's where significant figures come into play. And a significant figure consists of all the digits in a measurement that are known with certainty plus one final digit. And that one final digit is somewhat uncertain or is estimated. So if you're using a ruler, let's say, if you're trying to find the length of a pencil for whatever reason, and there's not a pencil on this, but it's just a red line. So you're trying to find the length of some item, and you have a ruler, this particular ruler. Now, if we were reading the length of this, we can only be so exact based on this particular measuring device. We can say for certain that this red line is between 5 and 6. We know for sure that this measurement is about 5 centimeters. However, we can estimate one more digit beyond what that's reading, and you'll see what the estimation is here. But if you look closely, we can say that this isn't really exactly in the middle, but it's about 5.4 centimeters. That 0.4 to the 10th place is somewhat uncertain. It's estimated. If I were to give this particular measurement and this ruler to everyone in the class, we'd probably all get 5 because it's certain that that's what it is. We know that. However, we're all estimating what that last digit is because our ruler doesn't read beyond that, but we have to estimate what it is. And that's really what significant figures is. It's that first measurement that we know for sure, depends on the measuring device, and the next digit, which is somewhat uncertain or it's estimated, you have to guess what it is. Other than that, we can't read beyond this 0.4. I can't say that this red line is 5.437500214 centimeters long because that's not, I can't read that far out according to this device. So therefore, this particular value, measurement, I should say, would have two significant figures. If I were to have this same red line and a different measuring device, however, and in this case, you'll see that we have measurements to the 10th place. So let's look. Again, for a fact, we can say that this is between 5 and 6. More so, we can say that this red line is in between 5.3 and 5.4. We can all see that. All of our measuring devices say that. However, we always have to estimate one digit beyond what our measuring device is reading, just like what we're doing with graduated cylinders in the lab. You always estimate that next digit, that one that's kind of uncertain, but you can technically see where it is. So we just approximate that. In this case, it looks like, now I didn't write this here, so I don't necessarily agree with this value, but it's 5.3, which is what we know. And this guy said it's about 5.36. So that 6 is somewhat approximated. And I don't necessarily agree with that because if you're looking at where that tip of the arrow is, it doesn't look like it's 0.6. It looks more like it's 5.38 or 5.39. But again, that's why we have to use these significant figures, is because there's some amount of uncertainty in measurements that we take. I might have something and another group might have something else, and a third group might have something a little bit different. And that's why we use significant figures. We don't just look around and, measuring things and with all of that. So when we're using measurements in chemistry, we have to be able to count the number of significant figures that measurements have. And there's 4 relatively easy things you have to look for. So the first rules, I should say. The first rule when you're counting the number of significant figures is that all non-zero numbers are significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, all of those numbers are considered significant in a measurement. For example, if I have the measurement 87, let's say, from here to, I don't know, Newark, New Jersey, I'm just making something up, is 87 miles. It's an approximation. It's not exactly 87, give or take. It's something else. That measurement would have 2 significant figures. The 8 and the 7 would be considered significant. The next rule. When a 0 is surrounded by non-zero numbers, it's significant. If more than one 0 is surrounded by non-zero numbers, the zeros being surrounded are all significant. So I like to say when zeros are sandwiched or when they're trapped in between 2 numbers that are not 0 makes them significant. For example, if I had the number 209, I have a solution. It's 209 milliliters. Again, it's a measurement. It's not an exact value. That 0 is trapped in between the 2 and the 9. Because it's trapped or sandwiched, that value counts, or that 0 counts. That number is important in that particular measurement. It's not always going to be important, the 0, but in this case, because it's trapped or sandwiched, it is. It's vital to that measurement. So that value has 3 significant figures. Here's the one that tends to get a little iffy with students, but I have a little trick that I think might help. When a decimal is in the number, the first non-zero number present and all the numbers after it are significant. So when you have a measurement that contains a decimal point, you have to look at where your first number that's not a 0 is. Head scratch. So if I have 9.70, the length of the pencil is 9.70 centimeters. My first number that's not a 0 is the 9, right here. In this case, everything after this is considered significant. So my 9, the 7, and the 0 is all significant. 9.70 centimeters. That means it's pretty darn close to being 9.70. Not exactly, because the measuring device might not be able to read after that, but there's some uncertainty in that. But it is relatively precise, 9.70. That 0 does count here. A little bit different as opposed to this value, this measurement, 0.004. This value measurement has only 1 significant figure. And I never truly grasped this rule myself, but the reason why it only has 1 significant figure is because these zeros in the front are technically placeholders. That's just the rule. We abide by the rules in chemistry, so that's how we do it. What I usually tell students is if there's a 0 in the front, put your pen down and cross out all the zeros in the front. And once you hit that number that's not a 0, in this case it's the 4, everything after that's significant. It doesn't matter if there's zeros after the 4. The only ones that don't count are the ones or the zeros that are before the 4. So this value has only 1 significant figure. Last rule. When a number is written in scientific notation, all of the numbers to the left of the multiplication sign are significant. So here's a value right here, 6.023 times 10 to the 23rd. You're going to get very comfortable, hopefully, with this number later on in the year. And if you're not comfortable yourself with numbers in scientific notation, I am going to post a video that shows how to convert between scientific notation and regular notation. So I'll link it down below so you can access that, but definitely check that out if you need some help with scientific notation and what that means, because I don't go over that in class at all, but it's a nice little crash course in scientific notation. So the multiplication sign is right here, right there, and everything to the left of that is significant. So in this case, this measurement would have 1, 2, 3, 4 significant figures. This doesn't count right here because those have to do with zeros. And again, zeros are not always significant. In fact, they probably most likely are not significant than they are. So the only number you have to really be cautious of are your zeros, because any other number is always significant. Let's do some examples here. I'm going to pull out the whiteboard and we'll do those together.
So following those rules, let's do sample problem 1, and let's just count how many significant figures are in each of these numbers. So I'll do up through n with you, and then I'll show you the answers for the rest of them. So A, 25.0. Notice there's a decimal point in this number, so we're going to have to look at rule 3. I'll just put the 3 up there so you know which rule to look at. So my first number that's not a 0 is the 2. And therefore, every number after that is considered significant. So this first number has 3 sig figs. You'll see me represent sig figs a lot with SF. Let's compare that to B. So how many significant figures are in letter B? Well, there's no decimal point here, so this has to deal with rule number 1. You just have to look at how many non-zero numbers they are. In this case, there's only 2. So this value has 2 significant figures. C, again, there's a decimal here, so this takes a look at rule 3. So when a decimal is in the number, the first number other than 0 is where you have to start counting your significant figures. What I always tell my students is put your pen or pencil down if there's a 0 in the front and cross out those zeros until you get to the first number that's not a 0. In that case, it's the 4. In this measurement, 4 is the only significant figure. Again, these guys here act as placeholders. I don't make the rules, so we're just going to follow the rules however we're supposed to follow them. But that's what those zeros are technically called. D. This one deals with rule number 3 also, because I have a decimal place. I have a 0 in the front. So again, put your pen down and you just cross out whatever zeros are in the front, because those are your placeholders. Everything after it is considered significant. This measurement would have 4 significant figures. Again, these all have to do with measurements. So keep that in mind. That's why we use this, is because our measurements can only be so exact. In math class, you never do this because they're typically not measurements. They're just numbers that you're working with. Put this guy down. 600. This one deals only with rule number 1. And in this case, well, you can also say 2, I suppose. This 6 is definitely significant. However, there's no decimal point in this number. So therefore, that 0 is not significant, and that 0 is also not significant. This is an approximation. This number has only 1 significant figure. Here's my most favorite example. I love the show My 600-Pound Life, right? I don't know if you guys have this guilty pleasure, but I love it. It makes me feel so good about myself. Not every person on that show my 600-pound life. Not every person on that show weighs exactly 600 pounds. It's an approximation. Some people might weigh less than 600 pounds. Some people might weigh more than 600 pounds. Therefore, that number is just an approximation. It's about 600 pounds. If the show was something like this, that number 600, I have a decimal point in the number. 1, 2, 3 significant figures. To find people that are exactly 600 pounds would be quite a difficult task to do, right? If everybody's 600 pounds, and I mean, it's hard to do in general because people's weight fluctuates every day. So it's going to be hard to find people to be on that show. If I have this number, holy moly, you're probably going to get nobody to be on the show because this particular value of 600, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 significant figures. Nobody weighs exactly that much. You probably fluctuate by the second when you're inhaling oxygen and exhaling carbon dioxide. That's why this number 600, this measurement, has only one significant figure. It's about that much. F. This one deals with rule number 3 again. We have a decimal. I have zeros in the front. I'm going to put my pen down until I get to the first number that's not a 0. 1, 2, 3 significant figures. Next one. Rule number 3 again. You're going to see lots with rule number 3 because most numbers have decimals in them. My first number is a 5 and I have a decimal. In this case, everything counts. Every number is considered significant. 1, 2, 3, 4, 5. G has 5 significant figures. H. Same thing here. Rule 3. We have a decimal point in the number. My first non-zero number is the 3. Everything after it. 1, 2, 3, 4, 5, 6. This value has 6 significant figures. I. Now, rule number 1. I have my 1 and I have my 5. So those are both definitely significant. However, I don't have a decimal point here. So this 0 is an approximation. This has 2 significant figures. This is like saying, oh, I have like $150 in my bank account. It might not be exactly 150, but it's about 150. 10.00. Decimal point. So we're going to look at rule 3. First non-zero number is the 1. Everything after it there counts. This has 4 significant figures. 3, same rule. Everything counts. 6. L, we're dealing with rule 4 here for the first time. So this one is written in scientific notation. So everything to the left of the multiplication sign is considered significant. If it's written in proper scientific notation, I want to make that note, which I will always give it to you in proper scientific notation. So L has 2 sig figs. M is also rule 4. We have 1, 2, 3, 4 significant figures because that's how many digits are to the left of the multiplication sign. Sorry about my ring light. Have to make these videos good. N deals with rules 1 and 2. No decimal point. This 7 and this 7 is significant because they're both not 0. This 0 is also significant. Why? Because it's trapped. That 0 is trapped in between those other ones. This 0 is not significant. At the end, that's more of an approximation. It's about 7,070. So this value has 3 significant figures. As long as you follow those rules, you should really be okay with this. Do the next few and I'll post the answers here so you can just check your work with me. So here's the answers for O through T. You can just check yourself. all the numbers that I underlined are your significant numbers in each measurement, and everything that I crossed out are not considered significant. If you have any questions, just mark them down on your paper and you can ask me the next time you see me.
Now, chemists don't just sit around all day and say, oh, let's just count the number of sig figs in each of these numbers. What a great day we're going to have. No, they need to know how to do that in order to do calculations with significant figures. That's really the prime reason why they do that. And this will tell you how to round in this class from here on out. So you don't have to say, Mrs. Snyder, I don't know where to round. How do I round? How many places after the decimal do I need? You'll never have to ask, because if you follow these rules, you should be good. You'll know exactly where to round your values out for every math problem. And there's really only two basic rules that you need to follow. One rule is for addition and subtraction. So, and it's a lot easier to do it than it is to talk about how to do it. So I'm just going to put this up here. You can write this down, and then we'll do a couple of examples together. So your answer will have the same number of digits to the right of the decimal point as the number with the fewest digits to the right of the decimal point. So again, we can't be more precise than our least precise value. That's the whole idea behind this. So we have to look for what value in either of these operations has the least number of decimal places after them. And that's how we're going to round the number. Let's do sample problem 1 on the whiteboard.
So in this case, we have an addition problem. So 7.939 plus 6.26 plus 11.1. A lot of times on paper, you're going to see them written like this, horizontal. What might make it a little bit easier is if you line up all your decimal points. So I'm just going to take this and rewrite it. You don't have to do this, but sometimes it helps. So there's that decimal point. There's that decimal point, and there's that decimal point. So notice all I did was I just lined those up, just because it makes it easier to see. Your answer cannot be any more precise than your least precise measurement. Again, these are measurements, which is why we are working with this. So if I was adding together the length of pieces of copper pipe to get the total length, if these were all inches, let's say, this ruler was not that precise because it only has one place after the decimal. So therefore, my answer can't be more precise than this least precise value. And again, that's because it only has one place after the decimal. So that's where I have to cut my answer off. However, before I start doing that, let's just type this in the calculator. 7.939 plus 6.26 plus 11.1. Calculator gives us 25.299. Now, here's where we're going to have to round. So here's my least precise measurement that has one place after the decimal. This is where I'm going to cut my numbers off right here. So we're going to round right here. So this has one place after the decimal. Forget about that one. When you're rounding, you don't have to look that many digits out. This 9, however, is going to round that 2 up. So your final answer is going to be 25.3. And if we were doing this, it would be inches, just to not forget the units. But your sample problem doesn't have units, so it's okay. But this would be your final answer. My answer can't be more precise than the least precise value. When we're adding and subtracting, the least precise value is the one that has the least number of places after the decimal point.
Multiplication and division, a little bit different, still not rocket science. So not too bad of a rule to follow. This one, you're not looking at the number of places after the decimal point. Instead, you have to look at how many significant figures each number has that you're multiplying or dividing in the problem. So your answer will have the same number of significant figures as the number or measurement with the fewest number of significant figures used in that calculation. Again, your answer can't be way more precise than your least precise measurement. You can't do that. So you can only be as precise as your least precise value. Again, I think it's easier to do them than it is to talk about how to do them. Let's go ahead and do a couple problems here.
And here's sample problem 3 with a multiplication example. So in this case, we don't care about the number of places after the decimal point. What we really care most about is how many significant figures each individual number has. So let's look at 27.2. This value has 3 significant figures. 1, 2, 3. This second value has 1, 2, 3, 4 significant figures. This value has 1, 2, 3, 4, and that's it. I almost counted beyond that. So your answer could only have the lower number of sig figs, which is 3. So that's how many I have to round my final answer to, is 3 significant figures. Let's just go ahead and perform this operation. 27.2 times 15.63 times 1.846. Calculator gives us this ridiculous answer. I'm just going to copy this down. So that equals 784.801056. If you write this number down, I start to get very anxious. So please round to your significant figures. It makes both yours and my life a lot easier. How do we round this guy? So it has 3 significant figures, the least precise. Well, 1, 2, 3, there's my first 3. I'm going to keep this 8, but all those numbers I'm going to drop off. Chop it off right there. That 8 is going to round that 4 up to a 5. So your final answer should be 785. The reason why I cross these numbers out is only because people will say, well, that 6 rounds that 5 up to a 6, and that was there. You don't have to round that far out. You just want to look at 1 digit beyond and then round that way. And then there's your final answer. And it's the same thing for division. Your measurement with the least number of significant figures is the least precise, and that's how many answers you should round your answers.